So in this lesson, after the previous lesson about ionic solids, we're going to learn about the properties of molecular and covalent network solids in terms of their structure and bonding. So by the end of the lesson, you should be able to explain the properties of these network solids and molecular covalent solids in terms of their structure. So molecular solids we'll start with first. An example of that is sulfur. So sulfur has a low melting point and does not conduct electricity. So why is this? Well, molecular solids are made of molecules. Again, it's in the name. And there are very strong bonds within the molecules. And we call these bonds intramolecular bonds or intramolecular forces. And they're very strong. However, there are then weak attractions between the molecules of sulfur, or in this case, carbon dioxide. And we call these weak intermolecular forces. So in terms of melting point, molecular solids have a low melting point and boiling point. And this is because the molecules are held together by these weak intermolecular forces. So even though the forces between the atoms is strong, the forces between the molecules are weak. This means that little energy is required to break these intermolecular bonds. The molecules themselves are not broken up, they're just moved apart from each other when they are molten or start evaporating. So in terms of conductivity, molecular solids do not contain charged particles. Therefore, because they don't have anything to carry the charge, they do not conduct electricity. In terms of solubility, this will depend on the polarity of the molecular solid and the polarity of the solvent. Polar molecules dissolve in polar solvents, and non-polar molecules dissolve in non-polar solvents. Like dissolves like. So something like methane, for example, will not dissolve in water because methane is non-polar from our previous lesson, and water is polar, whereas it will dissolve in a non-polar solvent. So that was molecular covalent molecules. We're now looking at covalent network solids, and the three examples we'll look at are diamond, silica, and graphite. So all three have very high melting points, and most, in the case of graphite it does, but most do not conduct electricity. So why is this? Well, in terms of giant covalent network solids, they are made of large networks of atoms, and they're arranged in 3D covalent networks, and there are strong covalent bonds between them. So you have strong intramolecular bonding and also strong intermolecular bonding. And they can come in three different forms. You can have linear chains, 2D layers, and three-dimensional networks. Very similar to the ionic bonding, which also had three-dimensional networks and correspondingly high melting and boiling points. And here's an example here of silicon dioxide, or silica. You have the silica atoms in red, and they are bonded to 3 oxygen atoms. Very strong intermolecular bonding, very strong intramolecular bonding, all covalent bonding. So in terms of the linear chains, you have infinitely long one-dimensional chains like the polymers, like your plastics, like polyethylene. And they have moderate melting and boiling points because they have strong intramolecular bonding, and there is reasonably strong intermolecular bonding between these long one-dimensional chains. In terms of the two-dimensional layers, the example is graphite. It's an allotrope of carbon, and so allotrope just means a different form of carbon, so you still have only the carbon atom, but it's structurally different, structurally arranged differently, and it's made up of sheets of covalently bonded carbon atoms. So in a sheet, each carbon is bonded to 3 others, and that forms 6 carbon rings. The next slide will show an illustration of this. So there are very strong intramolecular bonding between the carbons, these 3 carbons. However, there is that 4th position to bond, and that forms weak intermolecular forces between the 2-dimensional sheets. So each carbon atom uses 3 of its 4 valence electrons to form these covalent bonds. So it means you have 1 remaining electron, which is free to move. And because it's free to move and it's delocalized between the layers, free to move electron means it can carry charge because charge can move on these electrons. And here's a diagram. Here you have the two-dimensional layer where each atom is bonded to 3 other carbon atoms, and they are piled on top of each other like layers. And these layers can, because there's weak intermolecular bonding between the layers can slide against each other, so graphite is great as a lubricant for that reason. So in terms of graphite and melting, graphite has a very high melting point. It's about 3,600 degrees Celsius, and that's due to these 3 strong covalent bonds within the 2D matrix, within the 2D layers. Okay, and there's a diagram there of the graphite, so you can see the 2D sheets with every carbon bonded to 3 adjacent carbons, and they are on a layer of sheets where you've got the layers of these 2D carbon bonded. Okay, there's 3 carbons bonded to each other. In terms of electroconductivity, the only non-metallic element, carbon, that can conduct, and the only covalent substance that can conduct electricity is graphite. And that's due to this delocalized electron of the 4th valence electron, which is allowed to move freely throughout the network of layers. There's just a diagram there of these layers, like pancakes, on top of each other. In terms of solubility, graphite does not dissolve in water due to these strong covalent bonds. So the water can't get in there and break the intramolecular bonding and dissolve it. So in terms of the 3-dimensional networks, looking at silicon dioxide and diamond. So diamond first, allotrope of carbon, just like graphite, but instead of being in these 2D layers, it's actually in a 3-dimensional network. So every carbon is bonded to 4 adjacent carbons, and it's bonded covalently. And these 4 carbon atoms form a tetrahedral arrangement, which you can see on the slide there. And that's just a close-up of that arrangement. The atoms there, each individual carbon atom bonded to 4 carbon atoms, so strong intra and intermolecular bonding. So finally, looking at silica, silicon dioxide has a similar tetrahedral structure to diamond. However, in this case, each silicon atom is not covalently bonded to another silicon atom. It's covalently bonded to 4 adjacent oxygen atoms. So this means that 3-dimensional network solids have a very very high melting point due to the strong intra and intermolecular covalent bonding. For example, crystals of diamond will vaporize at about 5,000 degrees Celsius. They won't conduct electricity because there's no free electrons. No free electrons means there's no charge carrier, so no electricity can move through. And they do not dissolve in water because of the strong covalent bonds. There is no way for the water to break the strong intra and intermolecular bonding associated with these 3D network solids of silicon dioxide and diamond.